Welcome to our presentation on the Cooperative Transport Interface, where we've harnessed open source 5G OpenRan and virtualized PON networks to reduce latency and enhance resource allocation. This work is a collaborative effort between Trinity College Dublin's Connect Centre and Intel Corporation, Ireland. In this demonstration, we address the technical challenge of integrating optical and wireless networks, examining the traditional PON and its evolution towards a disaggregated architecture. We identified the efficiency gains possible by harmonizing the upstream scheduling of 5G NR and PON systems. The selection of appropriate PON OLT and 5G NR components was based on their compatibility with this integrated approach. We then implemented a CTI-compatible architecture, which allowed us to tailor 5G NR to better suit PON requirements. The execution of the demonstration provided tangible results, affirming the technical feasibility and potential benefits of this convergence. The key difficulty we face lies in the latency and inefficient resource allocation caused by unsynchronized scheduling between 5G NR and PON systems. Our objective is to mitigate these issues by introducing a synchronization mechanism that bridges the gap between the two, ensuring PON can effectively act as a 5G bearer network. We address this challenge with our Cooperative Transport Interface, a system that enables real-time dynamic coordination between 5G NR MAC and PON MAC schedulers. By harnessing open-source flexibility and virtualization efficiency, we have crafted a converged solution that merges optical and wireless networks seamlessly. Our live demonstration showcases this integration in action, with a virtualized PON DBA working in tandem with a 5G NR MAC scheduler to efficiently handle upstream PON burst scheduling. The demonstration's physical setup, utilizing a USRP X310 and Tibit PON transceivers, provides a clear live example of the potential for open source components. The use of passive optical networks, PONs, is a cost-effective approach for the delivery of ubiquitous broadband, since costs and capacity are shared across multiple endpoints. However, upstream scheduling requires a dynamic bandwidth assignment (DBA) mechanism which operates through a report grant mechanism in ITU standard XGS PON. While it's much more efficient than static bandwidth allocation, it introduces a latency of several hundred microseconds, which becomes an issue for application requiring end-to-end delays of 1 millisecond or less. This latency is further exacerbated when PONs are implemented as virtual network functions in modern implementations such as SDN-enabled broadband access (CBA) and when using virtual DBA. While these bring the required flexibility to fully customize a PON for high-performance multi-service and multi-tenant operation, the physical separation between hardware transmission equipment and software scheduling algorithms can further increase upstream latency. The innovation focuses on synchronizing a PON virtual DBA and 5G MAC scheduler using open networking implementations. PON and 5G NR systems typically operate independently, leading to suboptimal resource allocation and data transmission delays. This integration can be complicated by lack of alignment in standards and technologies. The innovation involves two sequence diagrams for non-optimized and optimized scheduler scenarios. In the non-optimized case, a downstream 5G NR frame travels from the CUDU to the RU over a bearer network PON and over a radio network to a UE. The frame must wait for an opportunity to transmit upstream, called the dBRU opportunity time. In the optimized scenario, the UE upstream scheduling information is used to anticipate the PON DBA's upstream scheduling. The upstream bandwidth map, BW map, is included as normal in the downstream frame. The Tibit microplug OLT is a Ethernet switch and server pluggable optical line terminals OLTs for virtualizing networks. It integrates a SFP plus 10G optical transceiver with an embedded universal Ethernet to PON MAC bridge, allowing software configurable symmetric 10G rates compatible with both XGS PON and 10G EPON protocols. The device supports up to 128 subscribers and 2K services per OLT, enabling in-band management via Ethernet link OAM and digital diagnostics. We have chosen to use the Tibit microplug OLT for this proof of concept because it uniquely supports offloading of DBA requests and grants from slave to master OLTs in a mechanism called cascading within the same hardware environment. In our design, we availed of the cascading feature of the Tibit OLT DBA to consolidate upstream scheduling among multiple OLTs within a single Ethernet switch, or in our case, server framework. Typically, the DBA functionality is hard-coded into the hardware, but it supports a hierarchical master-slave cascading feature that allows collective upstream scheduling across multiple microplug OLT units. A designated Tibit module is responsible for orchestrating upstream traffic for all other OLT modules on the switch. We developed a software-driven master DBA that overrides grant decisions made by intrinsic slave OLTs. This feature facilitates interaction between a software-oriented OLT DBA and a software-based CTI within a PON network built upon Tibit microplug OLT technology. The Tibit OLT DBA was integrated with SRS-RAN using Tibit's cascading feature to aggregate upstream scheduling across multiple OLTs within an Ethernet switch or server. ZeroMQ was integrated to facilitate real-time communication and efficient processing of grant requests, ensuring low latency communication between network components. The 5G upstream MAC scheduler grants were exposed to the PHY interface FEPI for coherent operation between the MAC and PHY layers of SRS-RAN. The Intel X710 NICSY's traffic steering capabilities were used to segregate user plane and DBA frames, minimizing buffering time and preventing scheduling delays. AFXDP address family express data path was implemented for fast, low-latency packet processing, enhancing data throughput and reducing latency in a telecommunications environment. The SRS-RAN software supports a functional split called Split 8, which is a non-ORAN configuration that locates the entire radio protocol stack in the distributed unit DU. This setup integrates with the Open5GS 5G core in the central cloud, facilitating end-to-end communication and data traffic management. The USRP hardware driver UHD is a software driver for Universal Software Radio Peripheral USRP devices working with SRS-RAN to handle radio frequency hardware. UHD manages processing of IQ samples for various communications tasks. To optimize SRAN Split 8, 2 adjustments were made to accommodate latency introduced by PON, increasing the maximum delay between reception and transmission in the lower SHWI layer and raising the maximum processing delay, allowing for greater latency between the DU and USRP equipment. The main objective of the presentation is to examine the integration of optical access and mobile 5G technologies through the utilization of open source and open networking innovations. This underscores the progression of RAN architecture in establishing connections with optical networks, as well as the Tibit XGS-PON pluggable OLT optical line terminal as a notable advancement in open network hardware. The presentation will showcase the incorporation of passive optical network, virtual dynamic bandwidth allocation DBA, with a 5G NR medium access control MAC scheduler. The practical implementation of the system will involve the use of hardware USRP X310, a personal computer equipped with a Tibit micropluggable optical line terminal OLT, and servers to support various mobile and packet optical network PON functionalities. The demonstration will emphasize the decision-making process for resource allocation in scenarios with the integration of CTI and situations without. The Split 7.2 architecture is proposed for a future experiment dividing the radio access network, RAN, into the radio unit RU and distributed unit DU connected via an open front haul interface. The DU is located in the edge cloud for low latency processing near the radio edge, while the central unit, CU, interfaces with the Open5GS 5G core in the central cloud for overall network management. This architecture offers granular control, improved efficiency, and support for advanced features like network slicing and edge computing. The Precision Time Protocol PTP Grandmaster Clock and Open Front Haul OFH are crucial components for synchronization and high precision timing across the radio access network. The PTP Grandmaster Clock provides accurate timing information for coordination, especially in applications requiring stringent timing. The OFH interface connects the radio unit and DU, ensuring low latency and high reliability. We would like to thank the support of grants from Science Foundation Ireland. We would like to thank Sienna on support of softwarization of cascading DBA functionality. We would like to thank Software Radio Systems through the use of their SRS RAN platform.